this system is air-water interface. We have DHDP more or less covered at the interface. DHDP is a surfactant which has -1 charge. And in the solution, we have monovalent ions, cesium and iodine. And here is a contour plot of X-ray fluorescence as a function of QZ. You might notice there's a big intensity change around this vertical line. Okay, this side is much light, this much is much heavier. And this vertical line basically is where the critical angle is. For the air-water interface is about 0.022 in both substrate. Okay. And on the left side of that line, basically the surface signal, and on the right side of that line is the above signal. So, and below the critical angle, we can see some emission line, but all these emission line from the element of cesium. And we could not find emission line from iodine below the critical angle. We only can see that when we are above the critical angle. So that means cesium is at the interface, but iodine is not. Well, that's not a big surprise because the cesium, the counter ion here, they like to go to the surface and bond with DHDP. But that contour plot probably is most direct evidence of counter ion absorption at the interface. Okay, now let's look at the right side. This system is a little bit more complicated. It's a mixture that has half of them are stearic acid, which is a -1 charge. The other half is stearoylamine, which is a positive charge. And in the bulk, we have calcium chloride solution. Okay, here is, on the bottom is the fluorescence spectrum below the critical angle. So this is the this is surface sensitive. Okay, how to get this one? Just imagine we can do a vertical cut along at any Q. So basically get the fluorescence spectrum at any Q. Okay. So if you look at this red squares, it's basically if surface is 100% covered by stearic acid, we only get a calcium signal. And if surface is 100% covered by stearoylamine, we only have chloride signal. So again, that's not a surprise because these are counter ions. But if surface covered by a mixture, half of them stearic acid and half of them are stearoylamine, we don't see any signal from any element. So the surface is completely neutral. Okay, here's an example of using this technique to study preferential binding. Here's our system. We have DMPA, which is phospholipid at the air-water interface. The DMPA is -1 charge. And in the solution, we have two kinds of divalent ions, and calcium and barium. So what we're interested here for this system is we want to see which counter ion like go to the surface more than the other. Okay, here is the data. That's X-ray for a spectrum above critical angle. So this is a bulk sensitive. And we have same concentration of calcium and barium in the bulk. But surprisingly, barium has much stronger signal compared to the calcium. It means one barium ion can produce a stronger fluorescence signal compared to one calcium ion. Or you can say barium has stronger fluorescence yield. Okay, let's look at the surface data. This is data below the critical angle. So this is surface sensitive. And let's just focus on this blue triangle symbol. This is a mixture. And you can see the calcium signal and the barium signal, they are almost the same. But we know one barium has stronger fluorescence yield. So this data tells us actually we have more calcium at the interface. Okay, you can easily imagine you can do the X-ray reflectivity on the same system. Most likely going to find out is some excess electrons underneath the head group, but you cannot tell these electrons from calcium or barium because X-ray reflectivity itself is not element sensitive. Okay, here let's give a quick summary about advantages of this technique, XF-NTR. So it can directly observe the existence and non-existence of target ions. It can also measure the preferential affinity for mixed metal ions. And probably more important is we don't really need to do any data analysis. The only thing we did so far is basically identify peaks and simply compare the peak intensity. So that's the advantage of this technique. Okay, it's all good, but can we do more than that? Let's say how many metal ions are at the interface. Here's our counter plot I showed you a couple of minutes ago. If we do a vertical line cut, we'll basically get a X-ray fluorescence spectrum at any given QZ. But if we do the horizontal line cut, like do a cut along the emission line direction, you will get a fluorescence signal as a function of the QZ for any emission line, like here for cesium and iodine. By modeling this data, actually, we can get how many metal ions at that interface. Okay, let's see how we calculate the fluorescence signal from the entire system. First, the fluorescence signal produced by a single ion is proportional to the X-ray intensity at this position, Z. And also have to take account of the absorption effect because the fluorescent beam have to go through the liquid and get to the detector. So it's proportional to e to the minus z over lambda f. Here, lambda f is the penetration depth of the fluorescent X-ray. So we talk about penetration depth for the incident beam. That's the penetration depth for fluorescent beam. X-ray intensity at this position is given by this equation here. So I0 is the income beam position. Basically, income beam intensity, basically it's before it hits the sample. And T, the Fresnel transmittivity, it's Mark already talked about yesterday. Basically, it's the magnitude of the transmitted wave. And also have considered the absorption of the incident beam. So this e to the minus z over lambda I. With these two equations, basically we can get fluorescence signal from the entire system. It's the integration of this integration of the intensity from single ion and ion concentration over the scattering volume here. And N is ion distribution profile. And C is the scale factor. We're going to talk about that later. Okay, so now we have two penetration depths in the equation. We can simplify that by redefining that as the effective penetration depth lambda. Okay. And also we did something in the hardware way. So basically we put a collimator between the detector and the sample. And with this setup, we can simplify the calculation of this integration.